All right, let's just dive right into this. Welcome to this explainer. Today, we're looking at an absolutely fascinating clash. We're going to explore what actually happens when pristine, high-dimensional mathematics collides headfirst with the rigid, totally unforgiving constraints of blockchain hardware. We are dissecting the orb swap compromise to see exactly how developers attempt to run continuous trigonometry on a network that fundamentally demands discrete math.
So here's our roadmap for today's descent to the metal. We'll start with the polar AMM dream, hit the determinism wall, and see why the network bans the FPU gambler. Then we'll uncover the emulation compromise, track the dangerous accumulation of observer debt, and finally reveal the true efficiency penalty.
Now, I want you to keep this massive, honestly kind of crazy question in the back of your mind as we go. How do you execute complex trigonometry, curves, sines, and cosines, on a machine that fundamentally rejects decimals? It sounds impossible, right? Well, this is the high-stakes engineering mystery at the very heart of modern DeFi. And the answer has huge implications for system efficiency and, ultimately, your wallet.
Section 1. The polar AMM dream.
Before we get into the hardware reality, we really need to appreciate the beautiful high-dimensional math that orb swap promises on paper. Notice the stark contrast here. On one side, we've got the academic ideal. Orb swap proposes using polar coordinates to rotate liquidity smoothly, creating these stunning n-dimensional superellipses. It's like drawing a perfect circle with a compass. But on the other side, we have the on-chain reality. Smart contracts are strictly confined to discrete, blocky integer grids. It's basically like trying to build that same perfect circle out of square Legos. The flawless theory of a continuous curve immediately hits the gritty reality of how blockchains actually process data.
Section 2. The hardware determinism wall.
To really understand why this beautiful math crashes, we need to move all the way down to the silicon level. There's a physical battle happening right inside your computer's brain over how math gets processed. On the left, we have the FPU gambler, the floating point unit. It's incredibly fast at running continuous numbers, but it's lossy, it's probabilistic. It guesses its way through complex curves using secret silicon tables. On the right, we have the ALU surveyor, the arithmetic logic unit. The surveyor performs exact, strict, 100% deterministic integer math. There's no guessing involved here. 1 + 1 is exactly 2 every single time.
Section 3. Banning the FPU gambler.
Now, Arbitrum Stylus is an incredible innovation bringing WebAssembly and Rust to the blockchain, which makes things vastly faster than the standard EVM. But to function on a blockchain, it absolutely must block native floating point math. Why? Because of something called non-deterministic drift. If you let the FPU gambler guess the math using secret silicon tables, different microchips are going to have tiny hardware-level rounding differences in the decimals. In a decentralized network where tens of thousands of computers must reach the exact same mathematical answer to maintain consensus, that is fatal. If the computers disagree on those tiny chopped-off decimals, consensus instantly breaks and billions of dollars in value would literally just vanish. So absolute mathematical reproducibility is mandatory, meaning the FPU is strictly banned. Section 4. The emulation compromise. This strict ban forces developers into a really difficult spot. To get those beautiful polar coordinates on-chain without the FPU, Orb Swap's developers had to make a tragic engineering choice. Let's walk through this painful translation process, the heavy penalty of Orb Swap's EVM compromise. First, developers write complex trigonometry in Rust, naturally wanting to use 64-bit floats. Second, they hit that absolute WebAssembly FPU ban we just talked about. Third, they are forced to emulate the math. They use software libraries, like PRB Math, to force continuous trigonometric curves into discrete integer approximations. They do this by multiplying values by 10 to the 18th power for WAD scaling, but here's the kicker. Multiplying sloppy emulated guesses by massive scaling factors doesn't fix the math. It actively ruins it. Section 5. Accumulating observer debt. Let's see how this builds into a massive systemic problem. There's a profound metaphor in the source material for this. It says, the FPU basically acts like a giant blender. You absolutely cannot reverse engineer that smoothie back into the exact fruits it came from. When you force complex trigonometry through emulated approximations, you experience this sort of wood chipper effect. The exact mathematical provenance of the financial data is permanently destroyed. The system is just guessing, rounding off, and chopping up the numbers.
And this leads us to a crucial concept, observer debt. This is the invisible accumulation of mathematical rounding errors created when continuous rational precision is forced into finite hardware bins. So when OrbSwap runs multi-coin pools with dozens of assets during extreme market volatility, this compounding observer debt makes the entire foundation wildly fragile. The emulated trigonometric angles stretch, the approximations widen, and the risk of a catastrophic precision loss just skyrockets.
Section 6. The True Efficiency Penalty.
All right, this is the climax of our explainer. Let's look at the brutal, quantifiable gas costs of this massive mathematical overhead. Just let these numbers sink in for a second. With stylus native integer math, basic addition and multiplication cost about 1 to 2 gas. That is incredibly cheap. But look what happens when you introduce stylus emulated soft float math to run those trigonometric curves. Basic addition spikes to 12 to 25 gas. Multiplication jumps to 30 to 60 gas. And division and scaling, they absolutely explode to 80 to 150 gas. Definitively, this massive mathematical overhead completely erases the intended efficiency gains of Arbitrum stylus. It causes gas costs to skyrocket, directly penalizing the user. But there is actually a better way. Bypassing the trig wall requires ditching these approximations entirely in favor of strict, discrete integer geometric rigor. Architectures like Lens prove that we don't need the FPU gambler or its really expensive emulations. By utilizing exact algebraic rings, specifically Pell-Smith rational coordinates, they map circular geometry directly to exact, division-free integer mathematics. No decimals, no square roots, just perfect deterministic geometric rotations. And the result of embracing that strict integer rigor? An absolutely staggering 74x reduction in metabolic energy. By stepping away from the heavy informational debt of emulated curves, systems can hit a hardware energy floor of just 0.05 picojoules per operation. This isn't just a minor optimization. It's a total paradigm shift that shows the absolute cost of clinging to emulating floating point curves. Which brings us to a final kind of provocative thought to ponder. Are we blinding ourselves to the true mechanics of these systems by focusing on the pristine academic theory and ignoring the messy, hard-coded reality? As we've seen today, the low-level execution details, how the silicon actually processes the math, matter immensely. Always question the hard-coded reality of the systems you rely on. Thanks for joining me for this explainer. Keep exploring, and I'll catch you next time.